Hello, with some of the deepest results in geometric measure theory behind us, we are ready to see some fruits of the efforts we have taken. I want to begin with this cute observation that the derivative of the area of a disk gives the perimeter of its boundary, which is the circle. Take derivative with respect to r, and you get that formula. In 3 dimensions, the derivative of volume becomes the surface of the sphere. And the same formulas hold in n dimension. I refer to Wikipedia for a discussion of n-dimensional balls and their volumes and also the area of their boundaries. We can get these formulas by induction using Fubini's theorem to go 1 dimension down. But I have a pictorial proof, or rather justification, of why this formula holds. Suppose we want to prove the one in 2 dimensions. Let FR denote the area of the circle or disk of radius r. To find the derivative, of course, you do a perturbation in the radius, you subtract the quantities, and you divide by delta r and let delta r go to 0. But here, the difference between the areas is this thin red strip around the circle. And if you cut it and open it, then it's almost like a rectangle. The error is negligible given the length is way larger than this delta r, the width. And how long is the edge of this rectangle? It's approximately the perimeter of the circle of radius r. Therefore, we can justify that the derivative of area equals perimeter. And notice that this will be almost the same for any reasonably nice set. If this is the interior, and if you add a little bit to the boundary, you move parallel to the boundary, the new area you attain will be this red strip along it. And again, if you cut it open and flatten it out, that will be about almost equal to the area of a rectangle with width delta r, or yes, and then the length equal to the perimeter of the region. But of course, this requires some regularity on how nice the boundary is and whatnot. Thanks to the coarea formula, we have a very general statement in this regard, and that reads as follows. Suppose you have a compact set in any Euclidean space, non-empty, and let d of x be distance of points to the set K. And recall that this distance is the infimum of distance of x to y, where y is picked from the set K. And it's a nice exercise that because K is compact, this is always equal to minimum. That means there is a particular y where this infimum is actually equal to dxy. So at least one minimizer exists for this. The claim then is that the volume of the region where distances, that is between distances a and b from your set, the volume of that part can be computed by adding up the perimeters of the sets that are constant distance to your compact set K. The corollary of this is that at almost every t, or here we have been using b, so b, the derivative with respect to b of this measure of the set, the strip at level a and b will be equal to, so integrating, taking derivative of an integral will be hn minus 1 of x's where distance x equals b. This is, if these were nice continuous functions, this would hold everywhere, but for just measurable sets, this holds at almost every b. So if you integrate a measurable function, the derivative of that integral equals to whatever you're integrating at almost every point, which is exactly the pictures we had seen above. Okay, let's see that if k is a singleton, say 0, then you get the circle and the disk. So the region, so here becomes d of x equal to a constant t is a circle, and the region, say, from level A to B will be the strip here. So this is saying that the area between strips A and B is equal to integrating the perimeters for all that range. So you see that even with k is just a singleton, this is already an interesting thing. And as soon as k becomes 2 points, say x1 and x2, say in R2, then the set of points that are the same distance to the set k will be, okay, so let me first draw two circles, hopefully. Let me first draw my circles and then I can decide about their centers. Okay, suppose this is my point x2 and this is my point x1, and radius of these circles is equal to t. Then the set where distance to the set k is equal to t is this set plus that, just this region. So the red part is the set of all x's in R2 whose distance to k equals t. So the parts of the circle we don't pick is because there, in fact, the distance is less than t, because those points are closer than t to the other point from k. Another observation here which will be useful to make at this point is that except for these 2 points here and here, it looks like a smooth, nice manifold, but in those points there is this break, and we will see that in general those points do not occupy too much of area. They form a null set, and those are exactly the points, the 2 points are where distance x to k is realized by more than 1 point in k. For every other point, there is a unique y from the set such that distance of x from k, distance of x from, for every other point x, there exists unique y such that it realizes the distance to the set. right? For example, let me do a green color, or blue, maybe blue more visible. If you're at this point, there is a unique point from your set which tells you that the distance to the set is t. The distance from the other point is not minimized. But if you are at this point, then both of these points are minimizes for your set. Okay, what we do next is prove a lemma, and then use that to prove the main theorem that we had above. We deduce it from the coarea formula, but we have to do a lot of work. So lemma 1, which deserves to be called more than a lemma, but there are stronger results than this, which I don't want to enter, at least in this video. The set of points, let K, other than empty, be any compact subset of Rn. Then the set of x's in Rn for which distance of x from K is realized by more than 1 point. First of all, because of that exercise I mentioned above, there is at least 1 point in K which realizes this infimum as a minimum, but there are some points with more than 2 points in K that are minimum distance to x. Those set of x's form a null set. That's the lemma. So those x's for which there are 2 closest points in K or more form a null set. In the K equal to 2 points, we saw that the set of x's for which there is non-uniqueness is just 2 points, and they have L2 measure 0. But a more complicated example, again, will be take as your K, I didn't mention that, I didn't want that. So this set K, let's say it ends here. It's a compact set, and the set of points which are, so if you are right in the middle, then there are 2 points which minimize the distance. So there is y1 and there's y2. And if you are here, again, there are 2 points minimizing the distance to the set. And so everything along this path will be among the points, Okay, so everything along this will have more than 1 point realizing the minimum distance. It is a more significant number of points compared to the previous example, but it's still L2 of this set is 0. Okay, we will deduce this theorem from Rademacher's theorem, and that is quite nice because I don't see any other easy ways of proving this. The stronger results that I alluded to are saying more than just, so here we're claiming that ln of this set is 0. The stronger results say that actually they go 1 complete dimension down. So the sets are something like Hn minus 1 rectifiable. They are contained in countable union of graphs of functions defined on Rn minus 1. So they almost go 1 whole dimension more down. So the set of points with non-unique minimizers is actually way smaller than just being a null set. Anyway, we don't want to prove that. We want to prove just that this set is a null set using Rademacher's theorem. Okay, and the way we obtain that is, first of all, claim number 1, this function, I want to switch notation from dx to fx. So this guy, which is going from Rn into R, well, in fact, this is 1 Lipschitz. Okay. The mini proof of that will be, so suppose you have f of x and you want to compare it to f of y. So f of x will be the infimum of distances of x to z's, where z is from your compact set K. By triangle inequality, for each individual one of these items, that means before you take the infimum, you can apply the triangle inequality, and this will give you x from y plus y from z. But then notice that distance xy, so I have fixed x and y in Rn. Because this quantity here, the first term, is independent of z, we can put it outside the infimum, and this will be infimum of z belonging to K, d of yz. But now y is fixed, z is from K. By definition, this is d of xy plus, isn't that f of y? It is. So we concluded that f of x minus f of y is less than or equal to distance of xy. By symmetry, x and y, we shouldn't distinguish between them. So if you change the role of x and y, you get that, in fact, the negative of that is also less than that. So f of x minus f of y is less than or equal 1 times distance of x and y. So that's the end of the proof that it is 1 Lipschitz. The consequence of this will be f is differentiable almost everywhere on Rn. It has a gradient. Okay. Claim number 2. It's not a claim, so it's just part 2 of our analysis. Fix x in Rn, and suppose C in K is such that we know at least one C exists, such that d of x from C is actually the distance of x from the set K. It's the minimum among a minimizer. So C is not the unique minimizer necessarily, as we have seen in the examples. But still we will prove something about this. So there is this magical K somewhere. Here is C, and here is our X, and C is closest point from K to my X. What I look at then is this line segment joining X to C, and I can always parameterize this, so this can be the point Tx plus 1 minus Tc. So let's call this maybe x sub t. When t is 0, you are at C, and when t is 1, you reach x. So it moves in this direction, positive t. Okay. Now, claim is that distance of xt to the set k equals t times distance of x to k, which is just distance of xc. Okay, why? You can always pause and figure out things for yourselves before seeing the rest of the video. Okay, for one thing, d of xt from k is less than d of xt to c, because c is just 1 point from k, and dxtk is infimum of all such things, so it cannot go larger. But this distance is exactly t times distance x and c. When you go from 0 to 1 with t, you go distance 0 to distance x xc, the whole line segment's length basically. And everything changes linearly, you don't even need to write down anything. So this is exactly equal to t dxy. Now we have to do the reverse one. If d of xtk was strictly less than t dxc, suppose magically some point appears here and it's closer than c to xt, then what we can do is we take this path, and then distance of x to this point would actually be strictly less than distance of x to c, which means that we have found the wrong c in the beginning, and that's the contradiction. If this was the case, then by definition of this distance, there exists some c tilde in k where distance of xt to c tilde is strictly less than t times distance of xc. But now, distance of x to c tilde by triangle inequality is less than distance of x to xt plus dxt c tilde. I'm just following my picture in my mind. This one is strictly less than t dxc, and xt and c tilde, sorry, the next one would be this. The x and xt are along that line segment joining them, and this will be 1 minus t. Just go back to the picture. D of xc, this will be this fraction of the line segment, and this will be plus t d x and c by the choice of c tilde. And this strict inequality is because the second inequality is strict. Actually, this is equality and this is strict. So this would be, which is equal to d of xc. Now we have proven that this is strictly less than that. And this would mean that we have found the better point, closer point to x than the original c, is less than and not equal to distance xc, which is a contradiction because we had chosen c to be the minimizer. Okay, so what did we prove? We proved this claim that along this path we know all the distances. Something curious here is that even if x has a unique minimizer, for these new points there might be other minimizers. So we know the distance, but we don't know if c is the only minimizer as you move along the path. So we only know the distances. Okay, now let's move to part 3. Suppose f is differentiable is one of those points where at x, we know from Rademacher that almost every x is such a point. So we have ignored a null set. And if we prove that x has a unique closest point, well, let me do this. If we prove that k has a unique closest point to x, we are done. What I'm showing is that whenever the function is differentiable at an x, that x is among the points with a unique minimizer in k. Oh, okay, so how do we prove this then? It's basically contained in the previous lemma. If c is at this point, we don't know is a minimizer, then by previous claim, here is x, here is the c, compact set k here. We know all the distances along this line, and if you compute the partial derivative, so directional derivative of f, which is the distance function, in direction x minus c, we can compute, so we have to then make it a unit vector, and there are technical things there, so I want to avoid that. Instead say, well, how do you compute directional derivative? You multiply the gradient of x. Why does this gradient is well defined? Because I chose x among the points of differentiability. So if I multiply this by y minus, x minus c, that is, I'm computing partial derivative or directional derivative in that direction, this vector. From knowing the exact values of f along this line, which is just linearly depending on that, we see that it's distance x and c. Or just because we are in Euclidean space, this is this. Okay, assuming that c is a minimizer, then we have this. If c2, other than c, was another minimizer, then first of all, distance of xc2 would be just distance of xc, because both of them are minimizers. And by doing the same analysis to the point c2, gradient x minus c2 would be x minus c2, which is x minus c. Now subtract the two formulas. Amazingly, the directional derivative is never the same for different directions. That's the whole point here. Because gradient, remember, is showing the steepest ascent, and its negative shows the steepest descent, and then it turns like a clock, and you obtain every real number only once, which is contained in this argument that I'm about to write. So this guy dot x minus c1 minus x minus c2 is 0. But this shows that, okay, we know that gradient of f at x is not 0 because of this. Okay? Therefore, you're dotting a vector into another vector, you get 0. One of them is non-zero. Then okay, I wish to say that then x minus c2 must be equal to x minus c1. but I have to rule out why it's not perpendicular to gradient f. Okay. The thing is, actually, this vector here is negative of gradient of f at x. It's parallel to that. So I thought this computation would be enough, but now I have to rule that out. Well, because if you look at the neighborhood of x, you are moving in the fastest decrease direction if you move along this line. That needs some argument, but at this point I don't want to enter that. So in this small neighborhood of x, the fastest descent is exactly moving along this line, so it is pointing in the direction of the gradient. And from that you get this. So but this means that C2 has to be equal to C. And either you didn't start with this and you have a proof, or you started with saying that C1 and C2 are different, then you reach a contradiction. So if I had started with actually the observation that this direction is negative gradient f, then that would prove uniqueness of C, because you cannot move in any other direction, and also you cannot stop at the new point C2 here, or you cannot stop sooner or later. So C and C2 must coincide. But all of this hopefully has convinced you that if f is differentiable at x in Rn, then minimizer is unique. And we know that f is differentiable almost everywhere. So minimizer is unique for almost every x. So that completes this proof. A very nice result. Remember that an arbitrary compact set can still be very complicated. Counter sets are compact, for example, and I just drew a picture with 2 points. Just imagine having uncountably many points and looking at this set of points with unique distance to a k and things like that. So this is a very interesting result in its own. Okay. From the proof above, we also see the following. From basically this equality here, gradient f applied to this vector is bigger than that. That means that the length of gradient of f at x, okay, let's do this. This minus this is bigger than gradient of f of x dot x minus c. And we saw that this is equal to x minus c, and which is non-zero. So gradient of f at x, okay, x is not in k, in which case you get x minus c 0. And f differentiable at x, then you have this, so this is bigger than or equal to 1. but also because f is 1 Lipschitz, gradient of f of x, which is after all just this directional derivative, and if it's 1 Lipschitz, you get this. Therefore, for almost every x in Rn, but not k itself, f is differentiable at x, and the norm of the gradient of f at x equals 1. That's very important for what will follow. Okay, now proof of the main theorem, which you will recall once I prove this. You don't have to go back, or if you have downloaded the PDFs, which I always put in the descriptions, you can go back and check what that theorem was. Okay, let f of x be distance of x to k, and let a to be the set of x's whose distance to k is between a and b. Then now we're using another important theorem that we have discussed, the coarea formula. Integrating over a, the coarea factor, so in this case this will be C1 because your f maps into one dimension, and derivative is gradient, dln of x will be equal to integrating over the range of f. Here will be from a to b, the m minus n, here m is n and n is 1, of the level sets of t intersected with a, dl1 of t. But because of this, that this is equal to the coarea factor, so that's just 1, and integrating 1 will be ln of whatever set you're integrating over. So you get this equal to a to b. So maybe it's here actually, let me put R1, but if you are outside the range AB, you don't intersect A with the level set. So that's why this becomes this. And when you are in this range, intersection with A is not really needed because the set is actually contained in A. So that becomes this, dl1 of t. And that's the theorem that we wanted to prove. This is just the set of x's where distance of x to the set k equals t in our notation. So a very, very nice generalization of what we observed with the circles and balls. And for its proof, we needed Rademacher's theorem, we needed the coarea formula. Two deep results, but the benefits are amazing. This is surprisingly general. K is just any compact set, no regularity required. And that means basically every compact shape you have, if you fathom it, you can get area by adding up perimeters. Or the derivative of how the volume changes when you fathom this set equals the perimeter, which confirms our intuitive way of seeing it in this picture. Sorry for this fast scrolling here. So it is confirmed here then that derivative of area equals perimeter. This is what we have proven under very general conditions. Okay, so please do put your comments and questions below, and please subscribe if you haven't yet. Thanks a lot for watching today, and have a great day. See you soon.